The moment a tiny faint smudge of light was flagged by an automated telescope and chilly astronomers around the world paused. On paper, it looked like another faint newcomer in the crowded sky, but the path it traced and the speed with which it crossed background stars whispered a different possibility. This was not born in our sun's family. This little visitor, later named 3I/Atlas, would join an exclusive club of interstellar objects, only the third confidently identified after Oumuamua and Borisov, and force us to confront how little we still know about the material that drifts between the stars. Who found it? The discovery came from the Atlas survey in Rio Hurtado, Chile on July 1st, 2025, a survey designed to catch potentially dangerous asteroids, but that now handed us a rare scientific gift. What made it extraordinary was its orbit. Hyperbolic with an eccentricity far above one, meaning it was traveling too fast to be bound by the sun's gravity and must have come from beyond the solar system. From that first report, telescopes worldwide, professional and amateur, re-pointed data poured in, and the object's story began to be told in angles, spectra, and subtle shifts of light. The race to understand it was not just driven by curiosity. Interstellar material carries the chemical fingerprints of other star systems and possibly of the environments that build planets. When did this all happen, and why did it matter so quickly? The timeline is compressed because astronomy today moves at digital speed. Discovery on July 1st, 2025, rapid follow-up observations, recovery images found from other surveys that pushed the observation arc earlier, and then formal confirmation that the orbit was interstellar. Within weeks, the Minor Planet Center assigned it the third interstellar designation, 3I. Over the following months, observatories large and small monitored its brightness, its coma, and its motion. In late October, the object made its closest approach to the Sun, and then sailed past Mars in early October at a distance measured in millions of miles, close enough for spacecraft around Mars to catch images and spectral data that proved invaluable. That passing by Mars wasn't a matter of scientific theater. Being observed from a different vantage point in the inner solar system gave orbital refinements and spectroscopic windows that Earth-based telescopes alone would not have achieved. By November and December, stacked images from space observatories and ground-based giants like Gemini and Keck had begun to reveal the comet's coma, its subtle tail, and chemical signatures that surprised some researchers. The rapid sequence from discovery to multispectral imaging is why 3I/Atlas instantly became a focal point for planetary scientists and astrophysicists. Where did this object come from, and what does that location tell us? Pinpointing a precise origin for any interstellar object is difficult because its long voyage through the galaxy scrambles memory of its birthplace, but orbit reconstruction gives us a rough inbound direction and velocity relative to the Sunday. 3I/Atlas's incoming vector and hyperbolic excess velocity indicate it came from the local galactic neighborhood, not from some exotic distant corner of the Milky Way. That matters because the composition we measure, frozen volatiles, dust, and metals, can be compared to comets formed in our system to look for patterns. Early spectra showed typical cometary molecules like water, carbon dioxide, carbon monoxide, and cyanide molecules we recognize from solar system comets, but they also flagged unusual abundances, notably a stronger than expected nickel signal reported in some analyses. The idea of a metal-rich plume or higher than normal metallicity prompted headlines and speculative theories, but as with every extraordinary claim, the data needed careful calibration and independent confirmation. Space agencies coordinated to cross-check spectral lines from different instruments, images from probes at Mars, along with telescopes like JWST and ground-based spectrographs, helped map composition across different wavelengths. That cooperative mapping is how we move from a single startling observation to a robust scientific conclusion. Why does 3I/Atlas matter beyond the immediate novelty of being interstellar? Because every interstellar object is a direct sample, however distant and remote, of planetary formation elsewhere. Comets are time capsules. Their ices and dust lock in the chemistry and physical conditions of the disks they formed in. If 3I/Atlas shows different ratios of volatile ices or unexpected metal content, that challenges models of how solids form and evolve in protoplanetary disks around other stars. More practically, this object became a testbed for international scientific coordination. Multiple spacecraft, orbital assets, and ground facilities aligned observations in different spectral bands and geometries. The result was not just prettier pictures, but complementary datasets that reduced uncertainties. Another dimension is the cultural one. Speculation attracts the public and the press. At times, high-profile scientists suggested exotic explanations, even mechanical or technological origins, which the broader community quickly scrutinized. The scientific consensus remained grounded. Natural explanations are overwhelmingly more likely, and the data so far align with a cometary body exhibiting some unusual, but not inexplicable traits. The episode showed how rapid public speculation can run ahead of careful analysis, and why transparent release of data and methods matters. How did scientists actually piece together the story of 3I/Atlas step by step, and what comes next? First came detection and preliminary astrometry. Timestamps and positions reported to the Minor Planet Center. Then, recovery searches folded in older images to stretch the observational arc backward, refining its velocity and confirming the hyperbolic orbit. Spectroscopy across visible infrared and ultraviolet bands followed each wavelength, revealing different molecules and physical conditions in the coma. Images from varied vantage points, including Mars orbiters, provided parallax and contextual views of the tail and any anisotropies and outgassing. Modeling groups then ran thermophysical simulations to estimate nucleus size and activity, while orbital dynamicists calculated the interstellar trajectory and probable future path out of the solar system. Alongside the technical work came vital peer review. Independent teams reprocessed raw data, compared instrument calibrations, and debated statistical significance for unusual signals like the nickel abundance. Science moves by skepticism and replication. Extraordinary claims require extraordinary evidence. Looking forward, records and spectra collected during this brief transit will be mined for years. Every interstellar visitor teaches us more, and 3I/Atlas has already sharpened questions about how common metal-rich comets might be, how protoplanetary chemistry varies across stars, and what observational strategies we should prioritize when the next interstellar traveler arrives. The final takeaway is not a sensational answer, but a clearer method. Spot it early, mobilize diverse instruments, share data fast, and let careful analysis rule the day. Sources and core reporting used for this script: NASA science pages and Atlas Discovery ReportingSpace.com and other science outlets, synthesizing follow-up Wired and Reuters coverage of NASA's multispectral releases and the community response, and ESA updates on orbital refinements.